Okay, students, good evening. Can you hear me?
Yes, sir.
Yes, sir.
Thank you. Yeah, today is a special day school. I want to do a little bit of teaching. Then I want to clarify a few things for you. And especially last time we were doing tunnel surveying. And we did it up to 3.93. We didn't do 3.93. We did it up to 3.9.3. Now today we are going to start it from that point onwards, and we will be doing until we come up to 4.71. We will not do method of correlates, but up to method of correlates we will do. So the exam has been set up to this point, and exam is a very easy one. It is a MCQ paper. You can fully utilize your book one for that. I think all of you have the copy of this block one. It is essential to write the exam. So get ready with your book, and you have to read it and get ready. Otherwise, it might be difficult for you to find answers within the stipulated time. So we will start from 3.9.3. So I'll share the presentation. Right now we did all these things, and so we have to start with this method of 2 wires in a single shaft. Now we were discussing method of 2 wires in 2 shafts, okay, but there are certain instances in tunnel surveying where this is not possible, because especially in deep tunnels, they might have only one shaft, and some of the leaning tunnels, they might not have an end, right? Like diamond mines, like graphene mines, graphite mines in places like that. So now this is a case where we use 2 wires in single shaft to transfer the coordinate system and to do accurate tunnel surveying. Now, under such circumstances, you can read here, 2 wires in one shaft system, which is called Wisbech triangle, is used to transfer the coordinate system underground. Usually, it is the national coordinate system of that particular locality. You need to establish a reference line within the tunnel system. The bearing of underground reference line in this case along a parallel line needs to be established. So you will understand most of these things when it comes to next slide. Now here, this diagram shows, actually it is figure 3.13 in your book, the entry and the end of a single shaft. Now there are 2 wires hanging from this shaft collar. Collar is the edge of this shaft. There are props which are directing towards the middle of the shaft, and they are hung from those collars. Now you can see there are 2 wires hanging from the top to bottom, and the coordinate system or the national coordinate system in the country has been established to this point P, and this point is a very close point that has to be established very close to AB, and from that point onwards we are trying to establish an underlying reference line called UV here, which are based on civil sealing stations, and we are trying to transfer the coordinate system underground. Now you can see what we do here is to transfer bearing of PQ to bearing of AB, and from that we are trying to transfer bearing of UV. So you need to understand what the bearing is, because bearing has been taught to you under surveying 1. That is the angle measured clockwise from the north to a particular arm or a branch, right? So you have studied the bearing in your surveying 1. Now, when we are establishing this AB 2 wires hanging in the shaft, these factors you have to pay very close attention. AP is less than AB. Now, this P has to be as close as possible to A, so that PA will be less than AB. Then the angle APB should be as small as possible. Now, APB, this angle here has to be small as possible. This angle here has to be small as possible. And then the third one, AB should be as long as possible. Now, this is the shaft. Now, these 2 points has to be located at the maximum distance, most probably through a radius, right? Through the center on a radius. Now, then UB is less than AB. Now, this UB has to be less than AB. Now, this U and V are 2 stations that we are going to mark on the ceiling of the tunnel. And now we have to mark it in such a way that UB is less than AB. Angle AUB should be as small as possible, AUB. Now this angle also has to be much as possible. You will understand why that is. Now here, this exercise given under this figure is the method that we transfer the bearing of PQ here to UV. You can see now the bearing of PQ is found with respect to north, and the bearing of UV has to be found, right? If you know the bearings with reverse calculations, which you have done in surveying 1, we can calculate the coordinates of U and coordinates of V with respect to the coordinate of P. That is, of course, belongs to traverse calculation. Traverse calculation, you have done it with respect to bearing. If you know the length of a traverse, you can calculate the coordinates of U and V. But let me explain you a little bit on this point. Now I will stop sharing this and I'll switch on the camera. Please let me know whether you can clearly see this whiteboard. Can you see the entire board? Can you see?
Yes, sir.
Okay.
Yes,
good.
sir.
Yes, sir.
Good. Now, few points which were not there in the PowerPoint presentation, I'll try to explain you now. I think you know the sine rule, right? Now, if you have a triangle, can you see this? Can you see?
Yes, sir.
Is it clear? Can you
Not
see?
clear.
Is it clear for you? Not clear? Just tell me. I just want to know.
Not clear, sir.
Okay. Then tell me whether this is clear.
Yes, sir.
Can you see?
Yeah. Yes, sir.
Okay, good. Now, can you see this letter size? Can
Yes,
you,
sir.
Yes, sir.
Can you?
Yes, sir. Yes, sir.
It is letter A, right? You can see it, right? Because I am going to use the same size of letters. Okay. Now, let's say this is B, C, and if this is A, by convention, we use simple letters for angles, right? And let the sine rule is AB over sine C equals AC over sine B equals CB over sine A. Okay? Can you see this? This is sine rule, right? Now, in case if you want to find sine C, let's say sine A with respect to sine B, so you can simply find sine A equals AC, AB over AC into sine B. Okay. Now A can be written in this form, right? A equals sine inverse AB over AC into sine B. Am I right? Just a simplification of sine rule, right? Now, having that in mind, let's proceed with the PowerPoint presentation. I think you can see the screen now. Now here, now if you consider this triangle of APB, this one, let me switch on the laser. Now, if you consider this APB triangle, if you apply sine rule, you can simply find this ABP angle, which is beta S here. Okay, please follow this in your book as well. Now, this beta S has been written in terms of alpha S, which is the angle between AP and PB. APB. Why it is been written in alpha S is that you can find the bearing of these two lines from north at point P. If you can find the bearing of PQ, of course, you can find the bearing of PA and PB, right? Since alpha S is small, you know, we can approximate the sine alpha S into alpha S, right? Then rest of that, we can find the bearing of BA here. From with respect to north, you can see P. Now, if you know phi, the bearing of PQ plus then the bearing of this entire now this angle QPB. Now this angle QPB also prevails here, right? Now at this angle and at this angle, then at another 180, then you will come up to this PB line, and if you add beta S here, you will get this equation. So this is the bearing of BA with respect to north, which is equal to phi PQ, and it gives this equation. For underground observations, you can find this the relationship between beta U and alpha U if you apply the same sine rule to this ABU triangle. You can see that there is a triangle ABU. Now, if you apply sine rule and if you find beta U with respect to alpha U, you will come up with an equation like this. This is quite similar to this one here. Since the alpha U is small, and I think you remember in the previous slide, we have selected this point in such a way that will satisfy our conditions. So you have to make sure that we will follow those conditions. Otherwise, our assumptions may not be correct. So you can write the bearing of UA in two forms. Now, bearing of UA, which is this line, can be written by adding bearing of this BA, right? AAP plus bearing of beta U. How can that be? If you know this angle, right? If you know this bearing, you can extend this line here, and you only have to add. I'll draw and show that. This is how it is. Okay. But you can see the entire board. Now in this case, we are talking about ABU triangle. It is something like this. Okay, ABU triangle. Okay, now you want to find the bearing of UA, right? Now you simply have to extend this line, right? Now if you know the bearing with respect to north, if you know this phi BA, what you need to know here with respect to north is this entire great angle, right? Now you know this angle up to here, okay? So you only need to add this angle here. Now this angle is what? It is beta u, right? According to the image. So if you want to find the bearing of UA, it is equals to the bearing of BA plus beta u, right? So is it clear for you? Can you see? I think you can see, right? So this is what it is. And similar bearing can be written in another form. That is by with respect to the bearing of UV inside, right? That is not difficult. And you can see here the bearing of UA can be found, right? If you know the bearing of UV, you only have to deduct a UV angle, this entire great angle from the bearing of UV. So you will get the bearing of this entire thing. So with this, you can find the bearing of UV by simply moving this AUV to the other side, or by adding this AUV angle to this, right? So you can substitute for phi BA what you have obtained here, and you can find the bearing of phi UV. So you started with the bearing of PQ, and you have managed to transfer it through PA, AB, BU, and UV. Now you can see it is a traverse. PA, AB, BU, and UV. Now, with the knowledge that you have in surveying 1 for traverse calculation, you can transfer the point at this point P to point U and point V. So you can find the coordinate system, coordinates of U and V with respect to the local coordinate system of the country. Now, that is the way that we normally practice. And there is another very interesting method, which is called gyroscope method. With this gyroscope, you can find the north inside inside the tunnel. There are 2 YouTube videos. You can find them once I send this PowerPoint slides to you. But let me show you what the gyroscope is. can you,
Well, hi, everyone, and greetings from Northern Michigan. This is Bob, the science guy. When
Can you
people
hear the
started
video?
to traverse the oceans, they did so in ships like this.
can you hear?
Yes, sir.
Okay, then I'll play the video for you.
Wooden sailing vessels. The old saying was, ships of wood, men of iron. Now, while indeed the vessels were made out of wood, they did contain an awful lot of ferrous metal. They had cannon, they had ammunition, even nails in the planks. This caused a problem for their navigation. Ships such as this used magnetic compasses, and this is an example of a magnetic compass. Now you notice that this compass has black metal objects on either side of it. These are magnetic compensators. This is actually tuned to the vessel to make that compass demonstrate magnetic north. And they're very sensitive. If you get those knocked out of kilter, your compass no longer points north. This became a much greater problem at the onset of the 20th century, when ships went from being constructed primarily of wood to being constructed primarily of steel. A solution to this problem had to be found. And the answer, as it turns out, was in the procession of the gyroscope. Let's see how they did it.
Solitary cloud. Shadow in the setting sun. And the last line. Honestly, can't even finish my haiku without being interrupted. Strider.
Well, guys, before we get started on talking about gyrocompasses, I want to clear up something that seemed to have caused a little bit of confusion. Now, if you look up here, you'll see that force equals mass times acceleration. Now, in physics, that is described as kilograms times meters over seconds squared. Angular momentum is very similar, except it's kilograms times meters squared over seconds. Now, when you're dealing with a force, the big difference is going to be how long you apply that force. Whereas in angular momentum, it is the length of the vector of the angular momentum that's important. Now, folks seem to have some problems with this diagram right here, and that's probably because where I explain the formula, that accidentally was cut out of the first video. Let me see if I can do it again. Now, say this is your angular momentum. It's in this direction, and it's a magnitude that's this long. Now, if you apply a force to this and bend it over 2 inches, just the tip goes over 2 inches, you're going to bend that angular momentum like that. But if you have something that's got a lot more angular momentum, like this, and you bend it over the same 2 inches, you notice it doesn't bend quite as far. The angular momentum does not want to be bent over, and the more magnitude that angular momentum has, the more resistant it is to being bent over. And this is one of the keys of gyroscopic stability. Both of these can come from the same gyroscope. The difference between the two is that this shorter angular momentum is not spinning as fast as the longer one. The faster the spin of the gyroscope, the longer the magnitude and the vector of that angular momentum is, and the more resistant it is to being bent over. Hope that clears it up a little bit. The faster your gyroscope spins, the longer or the larger the magnitude of the angular momentum, and the more resistant it will be to being pushed over. That was what this entire diagram was trying to demonstrate. I hope I've demonstrated that a little bit better now. Okay, guys, in our first episode, we talked about gyroscopic precession in a mechanical gyroscope. Now, I told you that there was a force that required the gyroscope to tip over a little bit. So let's go ahead and go over that. Say we have a gyroscope sitting on the Earth and it's pointing straight up in line with gravity. It will continue to point in this direction at all times. So as the Earth rotates, it will continue to point in that direction. But as you can see, it's now at an angle to the ground. As the Earth rotates underneath it, the gyroscope tilts over. Gravity places a torque on the axis of rotation. By the right-hand rule, a force is generated to the left, and the gyroscope begins to precess in a slow left circle. Okay, so let's go down to the equator, and let's look due east. Now, first thing in the morning, we see the sunrise. And what we do is we take our gyroscope and we lock it right on the sun. As the day progresses, the sun gets higher and higher. What our gyroscope will attempt to do is move upward with it, because due to angular momentum, the gyroscope will not want to tilt over. It will want to continue to follow the sun. It will point in the same direction, which was at the middle of the sun, as the Earth rotates underneath it. But what happens if we lock that gyroscope to the horizon? Okay, this is a little bit awkward for me because I've got the video reversed to make it easier for you, the viewer. Now, say I've got a gyroscope, and this is the direction of the angular momentum. Now, as you see, this is pointing east on our rotating Earth. Now, if I point this at the rising, a torque on this to hold that gyroscope on the horizon. So using our right-hand rule, I'm going to put the torque on it this way, and my thumb is pointing in the direction of the force. So what's going to end up happening is that the gyroscope will stay on the horizon, but it'll start swinging this way towards the north, because that is the direction of the force. Now let's see, probably the best way for you to be able to visualize this is to do it yourself. So I've got my 3 dots up here. This represents the rising sun looking east. If I take my pen in my left hand and I follow the sun as it goes up, it's going to move in this direction. If I take the fingertips of my right hand and place them on the end of my pen and force that pen back down to the horizon, I am putting a torque in this direction. That causes a force by the right-hand rule to my left. And as I'm looking east, my left will be north. Now let's turn around and do it with the setting sun. As the sun sets, the pen will be on the horizon. And then as the Earth rotates and the sun sets, it will attempt to follow the sun below the horizon. I take the fingers of my right hand, put the tip of that pen back pointing towards the horizon, and now the force is off to my right. Since I'm looking west, again, the force is to the north. So what we end up with, no matter what direction the gyro compass is pointing, whether it is at the east or the west, what will happen is the gyro compass will precess from both directions until it gets to the north. And that is the principle behind a gyro compass. The only time that that will not occur is if by some miracle you manage to get the gyro compass aligned perfectly with the South Pole on the southern part of the north-south rotational axis. Any other position will cause that gyro compass to rotate until it points to the geographic North Pole. Okay, so this is a Sperry Master Gyro Compass. This is located near the center of gravity of a ship to minimize rolling and the effects of the ocean. All it is a gyroscope that is locked to the horizontal. As we have seen that once this thing spins up, it's locked to the horizontal, and as a result, by the right-hand rule, it will cause that gyroscope to precess to seek true geographic north. Now, while we use the example of locking the gyroscope in on the rising sun in the morning, in reality, we don't need to lock this in on any particular celestial object. Gyroscopes, when they spin up, will have rigidity in space, and the angular momentum will point at a location in space. It doesn't have to have an object or a star or anything else there. It'll just simply point to a certain direction. As the Earth rotates, the gyroscope will attempt to maintain that direction. If the gyroscope is locked onto the horizon, that will cause it, due to the rotation of the Earth, to precess to the north, no matter what direction that it is pointing. Well, guys, there you have it. A mechanical gyro compass is absolute proof of the rotation of.
Okay, there are some videos in this presentation, but I'm not going to go through all of them. For a quick look, I will
The gyroscopic instruments include the attitude indicator, the heading indicator, and the turn coordinator. These are considered gyroscopic instruments because each one relies upon a gyroscope to function. They can either be driven by air suction or electric. By mounting the gyroscope on a response to a force. For instance, a small force is applied to the gyro whenever the airplane changes. Is that all gyroscopic instruments powered by the engine draws filtered air from the cabin through the.
You can watch these videos leisurely once I share the PowerPoint, and there are links in it. Please go to these YouTube videos and watch. So basically what it does is that it locks towards north due to physical the principles of physics, and with the help of that you can locate the north even within the tunnels, right? So nowadays we don't worry about these things much because we have very hi-fi instruments, but those days it was quite essential for them to find the proper north inside. Now I will move to the final part of this tunnel survey. Now it is about level transferring. I mean, this is not a very difficult part. Now if you know the level at a certain horizontal tunnel, you can simply transfer using a hanging tape in the vertical column, and you have to transfer that to the next level. Right now, if you want to find levels here, you can, using rise and fall method, you can simply find the level here. That's not big issue, right? You have to mount an instrument, you have to get the reading from the staff, you have to transfer it to the reading here, and you only have to measure the distance from here to here, and you can mount the instrument here. You can transfer this level to here, and then from there you can calculate the elevation here. It's no big deal. Now with that, we will finish tunnel surveying. Then after that, we will move into theory of errors. Now this is in level 4, and this is a very important lesson. I will go through it. Please read the note. I will try to explain the most difficult concept in this lesson, which is normalization of equations. Now every day when you do a measurement, especially in surveying, you basically do angle and distance measurements. Now there is a degree of error which could take place for every reading. So basically there are 4 types of errors. Now there is a definition, something called true error. Now in order to find this true error, actually to find true error exactly is impossible. Now for example, if you take a ruler or something, that needs, one second, I'll try to find a ruler for you. Now if you use a pen like this, right? If somebody wants to measure the length of this pen, right? Depends on the instruments that you're going to use to measure the length of this pen, okay? The reading will vary, right? It depends on the least count of the instrument. But it is impossible to find the exact length of this thing. But you can go up to a certain accuracy depend on your instrument, the least count of your instrument which you are using to measure the length of this pen. Now likewise, the difference between the measured value or whatever you measured as the length from its true value is called true error. So the difference between the measured value and the true value is called the true error. Then besides these true errors, the errors are classified into 4 categories: mistakes, constant errors, systematic errors, accidental or random errors. Now, mistakes, obvious, you know that if you do a mistake you can have an error, right? Now you can find the answer for this question from the book. What are the causes for making mistakes during surveying work? You know, you concentration lapse, reading errors, light errors. These things are mistakes, right? These things leads to mistakes. Now, then when it comes to constant errors, now these constant errors do not vary during a particular work. They have the same effect and the same algebraic sign for all observations. Now, the constant error is a constant error, as the word explains to you. It will repeat number of times that you do the measurements. Let's say if you're going to measure a distance with a tape which has a thermal expansion error, as you can see. Now, there is a standard temperature to use a tape, as you can see. Now this tape is expanded due to thermal energy, and you can see there is a positive error here. Now, if the temperature is lower than the standard temperature, so it gets contracted, and you can see with comparison to standard, there is a negative error here, right? But during the exercise, this error will be repeated. So it's a constant figure, but it will be repeated. Now, when it comes to systematic errors, so there is a system persists on these sort of errors. Now let's say you want to measure the distance at an angular ground. Now, if you measure this distance, this is wrong. So as you know, we always plot plans, right? So when we plot plans, what we need is horizontal distance. So we can simply correlate this measured distance to the planned distance with the help of this angle. Now this is a systematic error. So it has a system to convert the error and find the error. Okay. Now, when it comes to accidental errors, unknown errors over which an observer has no control, these errors occur with positive or negative values of similar magnitudes and equal frequencies. Example, imperfection of human eyesight, imperceptible changes in the instrument, indeterminate variations in the temperature, pulse. Now, accidental errors can be treated with theory of probability. Now, we can measure, let's say, if you measure a certain thing, let's say the length of this object, if you measure several times, let's say 100 times, you will have 100 answers. And you can distribute the measurements of your reading in a normal distribution. We'll talk about that. Okay. Now, if you measure the observation and the frequency of observation that you measure, and you will have a bell type distribution. Let's say you measure a distance. Let's say 10 times you get 100 meters. Let's say 50 times you get 100.5 meters. And you might get 101 meter maybe one time, right? Depends on. So these accidental errors can be treated with the theory of probability. Normally it comes up with this bell curve distribution, and if you calculate the error and draw it, this is the observational value, the error can be found with respect to mean. Now, let's say, let me draw it in the board and show you. Now you have a bell curve, something like that, for your reading, and you have the mean here, and you might have the current reading here, right? Now, the difference between these two is what you call error. This is mean, and this is your observation. Right? At this point. Okay. Now, if you plot this error versus frequency, what you will get is a symmetrical curve. Something like this. So this is the frequency, and here is the error. Now it can have positive errors or negative errors. Why? Because in that curve, we are going to calculate the error with respect to mean. Okay, so from this towards this side it is positive, towards this side it is negative, because the observation is always less than mean, right? So the error is normally found equals observation minus mean. Okay, so these things are there in your book. Please read them. Now you need to know all these statistical explanations, like what is arithmetic mean, standard deviation, then the error I have just explained you. Now the most important thing that you need to know is that if the deviation from the mean is more than 3 times the standard deviation, then the observation is rejected. Now in this case, you can find the standard deviation for each graph. If the deviation is 3 times more than the standard deviation, then such readings are omitted in the calculations. So you can work out this SAQ2, that is not that difficult. Then I will talk about principles of least squares. Now I will play this video for you. Just go through it. This is a very It's a very good video.
In this segment, we're going to talk about linear regression, and we're going to derive the expression for the linear regression model. So we're going to talk about derivation. Now, what regression is all about is that you are trying to best fit some given data. So let me write this down first, and then I'll show you graphically. So basically, it is that you are given certain data points. Let's suppose x1, y1, x of 2, y sub 2, all the way up to xn, yn. So you're given, let's suppose, n data points. And what you want to be able to do is that you want to best fit a straight line to it. And that straight line, let's suppose we call it y is equal to a0 plus a1x. That's the general form of a straight line. Y is equal to a0 plus a1x, but a0 is the intercept and a1 is the slope of that straight line. So what we're trying to do is that somebody is giving us these data points, and what they want us to do is they want us to best fit a straight line to this data point, to these data points. So let's suppose somebody says, hey, this is the straight line which you are drawing. So the equation of this straight line which we have is y is equal to a0 plus a1x. And this is, let's suppose, x1 comma y1. And this is, let's suppose, some x of I comma y sub I, some ith data point, let's suppose. And basically you're drawing showing all those n data points on this graph here. And then you are trying to draw a straight line to best fit those data points. Eventually what you want to do is you want to minimize the amount of difference which you have between these observed values, which are the ones which are given to you, and what the straight line will predict. Because you want to minimize the amount of difference between, but at the same time you have the differences at several points, at all the data points. You have a difference here, you have a difference here, you got a difference here. So everywhere there's a difference between what you are observing and what you are predicting. So the cross is the one which you are predicting, and the dot is the one which you are observing. And now this data point here, or not the data point, but the predicted value at that particular point will be simply a0, it will be simply a0 plus a1 times x of I. Because that's a straight line which you are going to find. And then if you put the value of x equal to x of I, that's what you're going to get for the predicted value, and this is the observed value. So if you look at the amount of residual, that's what it's called. Some people call it error. So there's a residual at each and every data point which you have, which will be the observed value, which is y sub I, minus the predicted value, which is the predicted value from the straight line. So you got y sub I minus a0 minus a1x of I. That is the amount of residual which you are having at each data point. Now what you want to be able to do is you want to be able to somehow make these residual to be small everywhere. And one of the criteria used is to simply take the summation of all the errors, square it, and then you want to add all those errors, the square of all the errors, and which is called the SR sometimes, and what it's the SR stands for sum of the square of residuals. And that's what you want to try to make as small as possible, because eventually what the goal is to minimize the amount of residuals. And one of the criteria which is used is called the least squares method of finding the regression model. And least squares means that you are squaring the errors and you're trying to add all of them and you're trying to minimize them. And that's why it's called least squares regression. So that means that it's summation of y sub I minus a0 minus a1 x of I squared. That's what you are getting from there. I is equal to 1 to n. So you want to minimize the summation there. Now you can understand that when somebody is telling you to do regression, you have these as the observed values, and this is what you're predicting. And the only control which you have is on these constants of the regression model. So these are called the constants of the regression model. And depending on what kind of regression model you're drawing, in this case we are doing a linear regression, so A0 and A1 are the two constant regression model. You want to be able to find those. Those are something which are in your control, and you want to control them in such a fashion that this summation, this whole summation becomes as small as possible. You cannot make it exactly to zero. If you make it exactly to zero, that means that the straight line has to go through all the data points, which is not going to be the case when you're doing regression. So you want to be able to make this as small as possible. So what that means is that we have to take derivatives with respect to A0 and A1, put those equal to zero, going back to your differential calculus class, to be able to minimize this expression there, minimize the summation here. So what I'll do is take the derivative of the sum of the square of the residuals with respect to A0, put that equal to zero, take the derivative of SR with respect to A1 and put that equal to zero. So that's what I'll have to do. And once I put those equal to zero, I'll get two equations and two unknowns. And once I get two equations, two unknowns, I'll be able to find what A0 and A1 are. So in order to be able to do that, I will have to take the derivative of this SR with respect to A0. So del SR with respect to A0 will be equal to summation 2 times y sub I minus A0 minus A1 x of I times minus 1 equal to 0. We are simply using the chain rule, so it's 2 times whatever is in the brackets multiplied by the derivative of this expression with respect to A0, it will be just minus 1. And then del SR divided by, with respect to A1, summation I is equal to 1 to n. Summation I is equal to 1 to n. So it will be 2 times y sub I minus A0 minus A1 x of I times the derivative of this particular quantity here, which will be minus x of I equal to 0. Because what you are doing is that you are finding out what the derivative of this quantity in the bracket is with respect to A1, and that will be just minus x of I. So we have set up two equations, two unknowns, so we need to be able to figure it out how we're going to solve these. So let's suppose if I call this 1 and we call this to be 2. So 1, what does it give me? It gives me, let me just expand this summation separately. I'll get minus 2 summation y sub I is equal to 1 to n, plus 2 summation A0 I is equal to 1 to n, plus 2 summation A1 x of I equal to 0. That's what I get from the first equation. Now what do I get from the second equation? Second equation again, I get minus 2 summation I is equal to 1 to n xi times y sub I, because I have y sub I here and x sub I here, so that's why I get that. Then plus 2 summation A0 x of I plus 2 summation I is equal to 1 to n. I'll get A1 times x of I square, because I'll have x of I here, x of I here. And that's what I'll get from there. Now I can see that 2 is common in here, so I can get rid of 2 here. I can divide both sides by 2. That's what I'm doing. I want to divide both sides by 2. And now since I see that here, this is a known quantity here, and this is also a known quantity here. But A0 and A1 are not, so A1 is right here. A0 and A1 are not known. A0 is not known here, A1 is not known there, A0 is not known there, A1 is there. So I'm going to keep those on the left-hand side of my equations. And this I will transfer to the right-hand side of the equations. So what I will get from there will be, the first equation will turn out to be I is equal to 1 to n A0. Then the second equation will turn out to be I is equal to 1 to n A1 x of I equal to 0. And the second equation, so that's my first equation. The second, not 0, will be summation of y sub I. The second equation will be summation I is equal to 1 to n A0 x of I plus summation I is equal to 1 to n A1 x of I square equal to summation I is equal to 1 to n xi y sub I. So again, now I got to realize that a0 and a1 are now constants because I have found those by taking the derivative of the sum of the square of residuals with respect to a0 and a1. So I can take those out, and you can realize, what is this? This is adding a0 n times, because you're doing a0 plus a0 plus a0 plus a0. So you're going to get simply this to be n times a0. So the first equation again can be written as n times a0 plus, I can take the a1 outside. I can take this a1 outside because it's a constant, so I can take a1 outside. So I'm going to write it like that. And then summation I is going to 1 to n y sub I. Then again here I can take a0 outside, so I'm going to take a0 outside. I get that. And then again a1 can be taken outside because it's a constant now. I is equal to 1 to n x sub I squared. And then summation I is equal to 1 to n xi y sub I. So basically I have two equations, two unknowns now, and I'm going to write them in the matrix form so that it is clear what the coefficient matrix is, what the unknowns are, and what the right-hand side vector is. And also it will help you to symbolically solve these two equations, two unknowns, whether you're going to use Cramer's rule or whether you're going to use any kind of Gaussian elimination symbolically. So all of those things can be done. Or you can just use your high school algebra to solve these two equations, two unknowns. In many of the books, you'll find out that many people drop this summation, these limits of summation from their books. The reason why they do that is because all the summations are the same so far as the limits are concerned. But I try to keep them because I don't want you to lose focus of that. This is, if let's suppose you're looking at this quantity, that this is a summation of the x of i's, all the x of i's are being added together. That's what that stands for. So I do keep the summations, but if you are looking at a book, please don't think that I'm doing something different. I'm just doing something which is more complete, showing you all the limits of the summations. So once you solve these two equations, two unknowns, which are written in the matrix form, this is what you're going to get. You're going to get a1 is equal to n times summation I is equal to 1 to n x of I y sub I, where n is simply the number of data points that you have. Summation I is equal to 1 to n x of I, summation I is equal to 1 to n y sub I. And then you're going to divide by n times summation x of I square, I is equal to 1 to n, minus summation x of I is equal to 1 to n square. And then a naught will be, you will get it to be summation y sub I is equal to 1 to n divided by n minus a1 summation I is equal to 1 to n x of I divided by n. So once you have found a1, you can find a naught by simply by this simple formula here. But what is this? This is nothing but the average value of the y's. So you get y bar minus a1, and this is nothing but the average value of the x's. You get x bar. So that's how you'll be able to find a naught and a1 by doing linear regression. Now, one of the things which you got to understand where people make a lot of mistakes is this and this. If you look at this expression where you are summing the square of the numbers, square of the x values, and here where you are squaring the summation of the x values. So these two are two different quantities. This is where you have to square each x value first and then add them all up. This one is where you add all the values of x, and whatever you get as a summation, then you square it. So that's something to be thought about when you are applying these formulas to develop the linear regression formula of y is equal to a0 plus a1x. And that's the end of this segment.
Okay, that sums up the linear regression equation. So what you need to know is this. Now,
Hello, I'm and welcome to the first tutorial for ECO 375. Today we are going
Now we can find the error of the readings that we have. Let's say we have 10 readings. Now for each 10 readings, we can find the error with respect to observation and mean. We can square it, multiply it by a weight, and the sum has to be minimum. So if we can select the mean, which makes this entire operation minimum, that is called most probable value. You can see it here. It is called the most probable value. This thing is explained in your book. This most probable value is the value that we create where the error becomes minimum, right? Most probable value. You can watch the other video leisurely. Now I'm moving into the other topic to calculate the most probable value of directly observed independent quantities. Now, when you say independent quantities, they don't correlate to each other. They have no relationship with each other. Now, this problem, I have taken it from your book. This is SAQ1. Now, with this exercise, you will understand now. There is an angle called 35 degrees, 21 minutes, 17.4 seconds, but it was measured only once. So they have assigned a weight which is equals to 1. Now this angle, the second angle has been measured 3 times. So they have assigned a value weight of 3. Now the third angle has been measured, this angle here has been measured twice. So they have assigned a weight of 2. So what do? They multiply each angle by weight, right? Then sum them together. Then the number of weights also sum, which is equal to 6. Then the summation of the multiplications is, it gives a certain value, 212 degrees, 7 seconds, 57.5 minutes. So you simply divide this by 6. And then you will get the most probable value of this independently observed, directly observed quantities. But it depends on the number of times that you measure. So if you measure this value, you can see the reading you have got is much more closer to this value than other values because it has a higher weight here. The next topic is about most probable values of indirectly observed independent quantities. Now, let's say these things are measured and one is calculated, right? Now, here the measured combinations are AB, BC, and ABC. Now you can find AC directly through calculations or by measurements. Now when you measure ABC here independently, you get these 3 answers here, right? But with calculations, by using these 3 equations, if you calculate the ABC, you can see there is a slight bit of change in measurements. You can see A, the value for A with measured, directly measured value is differ from the value for A. There is a difference in calculated value and measured value due to the errors in measurements. Now you can see A plus B equals 83 degrees also found with measurements, but A was also found with measurements, direct measurements. But you can see that there is a discrepancy between the calculated ABC and the measured ABC. This is due to errors. So we are going to mitigate such errors. Now, the there is a principle called normal equations. Now, you can get it the observed equations or the measured equations, and to calculate the most probable value, first we have to normalize these equations, right? So generalize these equations. So to do that, there is a technique that we are going to use. I'm going to use similar equations here, right? You can, I will stop sharing and start using the board for this work. You can see the board. Now, let's write the three equations. Let's say A plus B will give a different name, let's say L, right? Then B plus C equals M. Then A plus B plus C equals M, right? Now you can see the coefficient of each variable. Here it is 1, right? Here it is 1. Here it is 1, 1, 1, 1. This is an easy problem, right? Then you have another set of equations. A equals K, B equals T, let's say C equals 5. Another, now this LM, now this L, M, N, K, T, Y, all are constants. All are constants, right? Now you can see the coefficient of each variable in this case is 1. So to normalize, let's say to normalize each equation, you have to multiply. Let's say we are going to write the normalized equation for variable A, right? To write the normalized equation for variable A, what you're going to do is that you are going to multiply this equation by 1. Why? The coefficient of A is 1, right? Now, this equation we don't consider for normalizing for A because there is no A here. Now, this equation is multiplied by 1 again because in this equation, coefficient for A is 1. Let's say if it had 2, you have to multiply it by 2, right? But in this case, you have only 1. You have to use 1 multiplied by 1. Now, this will give you what? A plus B equals L, right? And this will give you A plus B plus C equals N, right? Now, this equation has only A and the coefficient for A is 1, and this is the entire equation is multiplied by 1. So you will get what you will get? A equals K. These two equations will not become important to normalize these 6 equations for variable A. So what are we going to do? We add these equations, right? We add all these. So we will have 3A, 2B plus C equals L plus N plus K. In your case, in the exercise, these L, N, M are constants. Okay, constant angles. You can add them up and you can have an equation. Now this equation. You can say N1. Now this is the equation for normalized equation. Can you see here? I think you can. Normal equation for variable A. Okay. Similarly, you can do the exercise for B. You can do the exercise for C. So what we will end up with having a set of equations which are shown in page 77. We'll do the same exercise once again. And you will have these three equations. First one, we got 3a plus 2b plus c equals. So I'll write the, I will give a constant k1. The next equation, now this is the normal equation for variable a. Okay. Now the next equation given here in page 77 is 2a plus 4b plus 2c equals k2 or something like that. This is for variable b, right? Then the next equation, a plus 2b plus 3c equals k2, k3, let's say k3. Now this is for C. These are all normalized equations. They are all normal equations generated. Right? Normal equations. Okay. Now, if you put it into matrix format, you will see that this is a very nice matrix. This is a symmetric matrix, right? 3, 2, 1, 2, 4, 2, and 1, 2, 3. And you can see the matrix is the symmetric one, right? A, B, C. And you have K1, K2, K3 here. Okay. So with this, you can simply solve this equation and obtain values for A, B, C. Right? Now, let's go to the presentation again. Somebody has asked a question. Let's see what. Now you can see in this presentation, these equations are obtained. These are the three equations. So the most probable values for A, B, C are found using normal equations. Now let's say the weights are attached to each measurements, as in the case of this independent quantities. Now here you saw that weights were attached, right? Now in the case of weights, you not only have to multiply it with the constant for the variable, but you will also have to multiply the equation with the weight, right? Now in this case, if for a plus b and a plus b plus c, if those two equation has weight 2, you have to multiply a plus b by 1, which is the coefficient of a, and also multiply it by 2 to obtain the equation, normalized equations, right? You can see this side also has to be multiplied, and you will have these equations, you will have to add it up, and you will have finally the normal equations with weights, right? Now, when you solve these equations using linear algebra, you will end up with these answers. Now, let's little bit talk about these residual errors, right? Now, in this case, you can see, let's say the residual error for a measurement A for most probable value is minus R1. Like that, let's allocate 3 residual errors for these measurements for A and B and C. Minus R1, minus R2, minus R3. These are the corrections. Let's assume that these are the corrections required to obtain the most probable values for A, B, C. Under such circumstances, you only have to substitute this value, which is A equals to this minus R1 into this equation, right? Finally, you will end up with another set of equations which are there to be solved. These are called reduced equations. You can see now in earlier case, we had to work with many large big numbers, right? Now you can see by simply putting a residual value, we have simplified our equations into much more workable, amicable equations, right? So what are we going to do? We are going to do the similar exercise. We are going to solve it for R1 and R2, but we have to assign for weights, and we also have to consider about the coefficient here, right? The coefficient of variable, right? So you multiply each equation accordingly, and you can find the normal equations for this R1, R2, and R3. And you can solve this for R1, R2, and R3, and you can simplify the ABC, because earlier we defined ABC in this way, right? You can see A equals 52 degrees, 27 minutes, and so on, minus R1, B equals 31 degrees, 26 minutes, 42 seconds, minus R2, likewise, you can see, right? And you can, you have reduced it, and you have got the normal equations, and you can find the errors, the residual values, and you simply have to substitute those residual values to find the most probable value. Now, in your book under section 4.6.9, I didn't put it in here because these are so lengthy. So instead of these numbers, they have used symbols, right? You can simply work out. Now, here at page 82, right? You will see that there is a special chart, right? Now, all these values are there to calculate the normal equations. So you can simply use this method. You can simply substitute values for these things. I'm talking about this section, right? From there are many big equations. There is no point of just copying it. You can just read it. Now we are substituting symbols instead of numbers. So finally, you can work out and you can come up with a table shown in this page 82. I think I have the soft copy of this. I will share that. Now under this 4.6.9, you can see the set of equations considered all line symbols. You only have to multiply it by W1, A1 for first one, because we are going to get the normal equation for R1, right? The second one, for second equation, you can see here, the coefficient for R1 is A2 and the weight for this equation is W2. So you multiply it by W2, A2. Likewise, you can multiply, add it and get the normal equation for each and everything. And finally, you can see for each coefficient, there is a order and there is a system. And you can sum it up and you can end it up with these figures, right? And you only have to substitute values. Now, let's say for this set of, in the previous case, the set of equation, you can simply substitute values for this W and coefficient. And you can come up with the value for normal equations and you can simply get the normal equation using these symbols, right? You can't memorize these things. You have to use the tables, right? That is how we normally get the normal equations when it is too complex to solve, right? So you can simply write a computer program for large number of equations to solve, right? You don't have to worry about it, right? Next, we will move into this 4.7, which is the last part that will be considered for your Cat 1, most probable values of condition quantities. Now, in this case, let's say you are measuring angles around a point A, B, C, D. Likewise, you can measure these angles. You can get the measured value. You can also get a conditional equation here, right? You know that the angle around one point, when you move, turn and come to the same direction, you have moved in 360 degrees. So A, B, C, D addition must equal to 360. This is a condition, right? Let's say you are measuring a triangle. The internal angle, summation of internal angles is equals to 180 degrees. Those are conditions. So when you are calculating most probable values for condition quantities, where the conditions are also exist, so you need to consider the conditional equations as well. So it will produce a most accurate, most probable value, right? So after that, it is just like in previous cases for residual values, you can simply substitute R1, R2, R3, and you can solve it. and you can end up with the values for A, B, C, D. Likewise, this is an example in your book. This is not a very difficult example if you understand the previous one. With that, I will wrap up the today's day school. I will be asking MCQs. Those are not very big mathematical problems. Those are simple questions asked based on your book, right? And for this triangulation, also few questions are, sorry, for the theory of errors, also few questions are included, right? Somebody has asked whether I will upload the record. Yes, I will upload the recording of this session, and I will upload the presentation files as well, so that you can go to those YouTube links and see. Now it is a question time. You can ask questions. Whatever somebody is asking whether there are any complex calculation, whatever the calculations which are there are workable within 4 minutes, right? Within 4 minutes, because you have to answer a mixed bag of questions. You will get 20 questions, right? Each of you will get 20 questions, and those 20 questions you need to answer within 75 minutes, right? So this is an MCQ exam. Don't mess with it, right? Because once you submit it, you can't do anything, right? No, triangulation is the next lesson, right? We have not done the triangulation. Also, we have not done this what you call method of correlates under this theory of errors. So that part I will do. So I will only ask questions up to 4.7, what we have just done now. Are there any questions? It's not a difficult paper because this is an open book exam and you need to have the book with you, right? And all the images I have used in the CAT paper are there in your book. If any image is not clear, you can simply refer the images in your book, which are directly used in the exam as well. So it is easy for you. Do you have any more questions? There is not available the last part of lecture 2 video in your YouTube channel. What do you mean? Which lesson? Can you just type which lesson? I'll check and let you know, right? So somebody is asking about environmental engineering. It's again 20 questions. Environmental engineering is very easy, right? So because you can directly use your book, right? And nothing to worry about it that much.
Excuse me, sir.
Yes.
So that additional 30 minutes are given to upload or something for that.
That's for
Nothing.
mode 3, not for MCQ.
Okay, sir.
MCQ, there is nothing to upload. You only have to tick it. And once you click finish attempt and submit, that's all.
Okay, sir. Thank you.
But you will get only 75 minutes. No nonsense. Okay. You have to be very careful with your time management. Are there any questions?
If we cannot submit the paper within the time, what will happen?
There's nothing you to submit. There's nothing. There's nothing you to submit. The question will come in your screen, right? Now, have you seen bullet list where you have to click the bullet, right? Likewise, you will get the questions. Okay.
Will it show the one by one questions, or in the same page there will be a 5 or 6
One by
page?
one, most probably one by one. Yes.
Can we go to the previous one once we?
Yeah, you
answer?
can. Yes. I think you can. Yes.
Yeah. Okay.
But don't play with it, right? Once you get it, you try to answer it, and let's say if you can't, that's not difficult because you have the book with you right now. Okay. Everything I have asked it from the book, right? I will guarantee and say everything I have asked in the exam is in the CAT paper is from this book, right? So you have the book with me. The best friend is with you. So what you need to do is to read this and come. So if you don't read, what will happen is that, oh, I have to find this section. And you will start turning the book here and there. And you, without knowing, you will lose time. Again, a person is saying, what are the lessons? Now I will type from lesson 1 to lesson 4.7 section. Okay. Now this what they have told us is that they will give you time. If your internet get disconnected, you will get the time from the point that you get disconnected in the internet. But I don't know how it works. Please try to get a good internet connection as much as possible, which is beneficial for you. Now, you know, we are doing this under a lot of difficulties like you are. So try to at least get a reliable internet connection for this exam. Okay. Normally, there is a stipulated time period that they will allow you to come back. Okay. I think they can monitor whether your internet disconnection, the loss of internet connection is a purposeful one or a fake, the actual one or a fake one. So don't try to play with it. Okay. Because they can simply detect you. Okay. So if you get disconnected, as soon as you are connected from that point onwards, that is what they told us. Okay. That is what examination division told us. Is it open learn page? What is that? It is open book. Open book means you are allowed to look at your book. Okay. You are allowed to look at your book. That is what it means. It's an open book exam. Do you have any more questions? Yes. Okay, then if you don't have any more questions, I will stop the class. And it is a easy paper. If somebody gets less than 50 marks, I will be very annoyed, because you can simply get 50 marks because it is from this book. Okay, right? Okay, good luck. Okay, good night.
Thank you very much, sir. Good night.